13.6 integrating vector valued functions. I think it's 13.6, but in any event, this is the second video for problem set number 6. We're going to make quick work with chapter 13 because we have a lot to do in 14 that's important, and also 15 and 16. Being introduced to these vector valued functions and the notation will serve us well when we get to line integrals, so that's why we're introducing it, so you're not so intimidating. We're going to look at an interesting calculus problem. It's really a differential equation we're going to solve. We have r double prime of t is equal to 0I minus 32j, and r prime of t is 20I plus 20j, and r of t is 0I plus 6j. And I can give you a scenario which would fit this. We have something being launched from 6 feet. That's the initial position. 20I plus 20j would be the initial velocity. We're launching it at a 45-degree angle. And this would be square root of 800, which is 10 square root of 8, which is 20 square root of 2. 20 times 1.4 is roughly 28 feet per second. So it might be 40 miles per hour or so. That's how fast we're launching this. It's a pretty good speed, slow for a major league pitcher, probably fast for a 5th grader. We're launching this into the air. It's going to follow a parabolic trajectory. This is the initial velocity. The acceleration, this is feet per second, negative 32 feet per second, or negative 32 feet per second squared. The question is, can we describe what's happening? And that's where solving the differential equation comes into play. Hi, sunshine. This is my kitty. I should launch her into outer space right now. No, I won't do that. Okay, come on, kitty. R prime of t is equal to the antiderivative r double prime of t dt. And the antiderivative cancels out one of the primes. And so we have integral of 0I minus 32j dt. And then here's how we do it. The integral of 0 is a constant. Then negative 32 is negative 32t plus another constant, j. We have two constants of integration. We just integrate these scalar coefficients. You could add a constant vector on the end, but this tends to make it a little bit easier. Now, there is an initial value. Sorry about that, my mistake. That should be 0, and that should be 0. My mistake. These are initial values, and so this is actually an initial value problem. It's called an IVP in differential equations, where this is the differential equation, these are the initial values. We have a second order differential equation. We need two pieces of information to fully determine what's happening. So now here's how we're going to find C1 and C2. We're going to use this information, r prime of 0, that says t equals 0. Well, we can plug 0 in for t right here. There's no t here, so we just get C1I plus negative 32 times 0 plus C2j. And we're going to set it equal to 20I plus 20j. This term, of course, goes away, right? And so guess what? We have C1 equals 20, C2 equals 20. And so we can substitute that in. We put 20 in here, 20 in here, and we have r prime of t is equal to, can't forget my vector, 20I plus negative 32t plus 20j. This is our velocity. This would be feet per second squared up here. This is feet per second. This is our x velocity, otherwise known as dx dt. This is our y velocity, dy dt. Uh, and you can check, you can take the derivative of this, and guess what? It gives you this right here. Next, we want to do a second integration. And this way we can find r of t. Let me come up here, make use of our space here. To cancel out this prime, we do another antiderivative. And so r of t is antiderivative r prime of t dt. And that's going to be antiderivative. Let's put all this in. 20i plus negative 32t plus 20j dt. And antiderivative of 20 is 20t plus c3 I. We can't use c1 or 2. We already used that back here. Okay. Plus negative 32 gives you negative 16t squared plus 20t plus c4 j. Okay, it probably looks familiar. Now, of course, we have to figure out c3 and c4. So r of 0 is given to be 0i plus 6j. And what we're going to do, you can set it equal to this, then substitute, or you can substitute, set it equal to this. Doesn't make one bit of difference. Let's substitute 0 here. We get 20 times 0 plus c3i plus negative 16 times 0 squared plus 20 times 0 plus c4j. And guess what? This goes away and we end up with c3i plus c4j. And we'll set that equal to 0i plus 6j. Okay, it's not always so simple. If there were sines and cosines in here, then not everything would zero out except the constants. In any event, you can see C3 is 0, C4 is 6, C3 is 0, C4 is 6, and so we have R of t is equal to, let's go back, R of t was 20t I plus, now over here we have negative 16t squared plus 20t plus 6j. Okay, and these are the position functions. This is really equal to x. This is really equal to y. You've solved these problems before if you've taken physics. In elementary physics, quite often you start with this. You plug in the initial velocity and initial position and everything, generate x and y, and then you go backwards. You take derivatives to generate the velocity and the acceleration. So, but this is how it's all derived. This is the natural state of things. The acceleration we know because we know what forces are involved. If you know the force, you know the acceleration, Newton's second law. This is what we know, this is what we could measure, and this is what we can derive, quite simply put. So, okay, there's one of these simple ones to do, and then there's also a derivational one. Don't be intimidated by the general derivation. You can put parameters in here, vi cosine alpha, vi sine alpha. They're just constants. Throughout the whole integration process, the only variable is t. All those other things are called parameters. They're treated like constants. And you can actually go through and derive an equation that you learn about in physics. That's the great thing about calculus and differential equations is you can derive all the physics and not just use and memorize the formulas. That's why it's no surprise Isaac Newton developed calculus and Newtonian physics. So Okay, that's all for this video.